Hello everyone, it's February the 9th, another late night. It's actually not that late. I was very sleepy. I actually fell asleep earlier, sitting on my chair, not really doing anything, and I just fell asleep. Alright, so let's see if we can do this fast. Alright, the first one we have is called summary sum equals k. Might have done this before. Oh, it's a new one. Oh, okay. Given an array of integers, and integer k, return the total number of continuous subarrays with sum equal to k. Ooh, interesting. Okay. Continuous subarray. And it's not like sorted or anything, so maybe we cannot use sliding window. Sliding window requires it to be at least follow some rules, right? So I know when to expand and when to decrease. This one does not have these rules, which means we have to figure something else. Okay, so as we go, equal to this k, okay? So when we start is 1, right? So sum 1 is, we have 1, right? Ending at here. So now looking at this one. So I'm having myself, sum 1, I have 1. And I'm looking at the one ahead of me, which have all this, ending at this, all possible, right? All possible sums. There are a lot of different sums. Anyway, let's say we have all the possible sums, and then they have number of counts, right? And if I say I go through everything and I'll plus 1, right? Now I update it. But then this thing will grow huge, 10 to the 4th. We have all different types of sum. All different types of sum. My end of memory. Well, we can try, but every time we need to copy the entire thing, because we cannot just change, right? Yeah, we can't just unless we no, we can't. And it's for every single thing. That's like O(n) squared. I think that's gonna time out this method if we keep keep a record of all possible sums ending at everything. I don't think that's gonna work. What else? Total number of continuous subarray with sum equals to k, right? So for each subarray, we're ending at a certain value. If I say I want to find the last, okay, like I say here is 1. So how many? If we have something that if something in the head that we can plus this equals to 2, so we need to find the total number that sum up equal to 1. So among these, right, Now, ending at this, ending at this, we're going to find sum up to 1. And for this, we need to find sum up to 1 and sum up to 2. And we add those together. Which it means for this, we're going to find sum to 0, sum to 1, and sum to 2. And for this, sum to 1 is 1. Okay, so back in here, sum to 1 is 1. Hold on, what are you saying? We have 1, 1, 1, right? So for element 2, this requires total sum to 1 in this thing, right? We have to say this will have sum to 1. So now, what I'm looking for here is we need to say sum up to 1. Well, it's myself, so I have 1. Right? Okay. Now we go to the front one, for this one. So this one, I need, so here my sum up is 2 and 1. So when we look front, I want the sum is 0 and 1. That's from the requirement from this. And this also required for 2. So 0, that's 0. 1, because already 1. And then say sum up to 1, I have 1, so I plus 1. And sum up to 2, which is 0. So now we add them together, so that result is 2. But that's still at each specific step, right? At each specific step, we are expanding. We are expanding the total possible sums. Well, if we find a range that's already sum to k, and I move on, it's too big. Do I ditch? Hold on. What if we do what if we do prefix sum on this? 1, 2, 3, that's the first one. So in order to find k, all we need to do is say we need a certain range, right? So we need some value minus the other value equals 2. So if we can put all these into a counter with their, so for 1, right, we need to find if there's anything. So 1, it will be the, hold on, it will be this minus this, so this will be plus 2. So we see if it is a 3. And yes, we have a 3, which means from this to this, and then we move on to this one. If itself is 2, and that's good, right? So from start to this, is this, and then from this to the end. This actually might work. Let's try it. 1, 2, 3. Prefix sum 1, 3, 6. We want to find 3. So 1 plus 3 doesn't exist. 3 plus 3 we have 1. And 3 by itself has 2. 6 plus 3 doesn't exist. So yeah, I think we can use prefix sum for this. And Python has something for this. I think it's from Beta Tools. Accumulate. Oh, we also need counter. So pre-sum counter. Okay. So we do this. I just realized something. That should be two different entities, because I need to iterate through the pre-sum, right? And then we say counter equals counter, pre-sum counter, okay? and then we say for, let's say p in pre-sum. That's actually pre-sum, not pre-sum counter, pre-sum, right? So we say this in pre-sum, every single one. We're trying to find counter counter p plus k, right? And plus boolean value p equals k. And we return a sum of this. Okay, let's give this a shot. So 1, 1, 1, 3, no, 2, 3, no, 2. 1, 2, 3, 3, 2. Nums k. Subarray. Nums k. Okay, let's give this a shot. Again, I'm gonna run this. I just do 1000, so too much. We make some I don't know. That's actually good. Let's try this. Maybe it should be 0. Not a valid type. Oops. And single one. And actually, I'm more interested in this. What else test case you can do? Let's try it. Wrong answer. Huh? Zero. Huh. Give Given this, I want to add up to 0. Shall be 0. I just 1. I count I have 1, right? And then 1 plus 0. And k can be negative. So you're saying if k equals 0, yeah, 0 is a special case. Which means 0, if I from here, right? 0 will be coming back to myself, which I shall say if k is equal to 0, then because p plus k will be p, I need to do this minus 1. Yeah, I cannot count the current thing. Minus 1. If k is not equal to 0, it's counting somebody else. Now we have to include all of them. So we should say this plus this minus blank k equal to 0. Maybe I think it'll be better. We just say if k equal to 0, right? So return minus 1. This one minus 1. Because k equals to 0, and then okay, edge case. Not sure. There might be other edge cases. For example, if we have 0 by itself, I think I found another edge case. If it's 0 by itself, it should be 1. Oh, hold on. I did get 1. Oh, I have this. That's pretty good. But if it's 1, how about 1 minus 1? Now let's hit a few zeros. 1, 1, 1. No. 1, 0, 0, 0. And 0. And of course 0, 0, 0. Say 1. Ew. 0, 0, 0. 2, 1, 2, 3, 4, 5, 6. I got 9. Oopsie doozy. We find something, huh? Find something. 0, 0, 0, which is 0. Should be 6. Exactly, that should be 6. But in my case, it's a 9. The k is 0, right? So everything is 3. And Jesus. Hmm. So I have 3. one with a p equals 0, and then for this, I add 2, and for this, I need to remove, because I consider on this already. I need to remove from consideration. So I think it will be easier. We just say rest equals 0 for p in pre-sum, right? And then if k is equal to 0, right, then now we say rest plus equal to counter p minus p plus k, right? P plus k plus boolean p equal to k, right? We can do this for sure, and if k is equal to 0, then rest into minus equal 1, because I do not want to count myself. And after I'm done, like after p is done, then we just say counter p minus equal 1. Right? This is to avoid double counting. Okay, what do you mean by double counting? If it's from here, I count here, and from there, I don't want to double count. So I do this, and return rest. And we say we do this because we don't want to double count. P plus 0 is p itself, and it has to move to the other thing, right? So if we don't count the current, don't count p at the current position twice. Only count it once. If we do this, then we pass. Okay. Maybe if we do this first, hold on, let me think. Okay, we're trying to do this, right? And I'm in this position, and I'll try to see how much this one has. So I can just do counter p minus equal 1 first, and then try to see how much I can get by p plus k. Because when I do p plus k, I'm trying to get to some value, right? And yeah, maybe I can do this. And then I can avoid this. Avoid double counting, right? Because I'm at the current p, because I'm going to count this p. And every time after I count this p position shall not be counted again, because I count from this adding k, right? So if in future somebody adding k can come back to me, or if I can come back to myself, that shall not count. So let's try this. Run this. Okay, try again. Yep. Not the best, but it works. I actually have a solution to this one. That's good. I'm pretty sure there's some smart solution. So I use prefix sum and a counter on the prefix sum. Then I iterate each element in the prefix sum array then I iterate. And I iterate the prefix sum array. For each element, I can check whether, for each element p, I can check whether p plus k exists in the prefix sum. If it does, then there must be a subarray going right from p to p plus k, and there must be a subarray in between, right, in between p and p plus k that sums up to k. Now the tricky part is to handle the case of k equal to 0 and nums containing 0. To handle that, I do counter p minus equal 1 before incrementing the result. So counter p minus equal 1 means that we remove the current position from consideration. This can prevent duplicates, right? This can prevent duplicates. Duplicates when either p plus k goes back to p, or some future value goes back to p. This makes sense. Hopefully it makes sense. On. Okay, this is on. Is on. Runtime is not that comfortable, but we did pass this milliseconds and 19% ranking. Okay, let's see solutions. Brute force on tripled. That's probably not gonna work. Using cumulative sum. On squared. Yeah, we get a cumulative sum, and then we do this, without space. Hash map. Oh, what do you mean without space? Oh, we modify nums. Nah. Wait, are we modifying nums? Nah, this is the one that I will go. Right, so we have the starting position, and then we just keep adding, and then we move to the next starting position, and then I keep adding. Yeah, this is like the one that naive solution, and this is on. Yeah, this is approach 4, right? Let's see if we are thinking about the same thing. Map.put 0 and 1. Okay, so doing this, if map contains key sum minus k, count plus equal to this. Okay, and map.put sum. So it is the same idea, but how does it avoid double counting? And you put a 0, 1 in there, you see that? The sum just a cumulative sum, it's nothing special. Nothing special. So we get a first sum and then we do minus, right? Sum minus k. Which is fine, we can do sum minus k. Here I'm just sum plus k. So sum minus k. I see, I can avoid this by, I can say counter 0, right? Plus equal to, oh, counter 0 plus equal to 1. Counter 0 plus equal to 1. Actually, no. This is minus, right? This is minus. That means if it's equal, then I minus, that's fine. Let's see how this one goes. So, as I go through, right, let's see the 0, 0, 0 case. Now I have a 0 coming in. And because 0 is 1, then result is 1, right? Because it's in there, result is 1. And I put sum. Now 0 becomes 2, right? So I have 2 is 0. So next one, 0. Minus k is 0. So which means previously, right? So previous, we have 2 zeros. And that plus 1, I have 3 zeros. And last one has 3. This is actually cleaner. We don't have to worry about this. What a minus? Wait, what's the difference between minus and plus? Shouldn't be any difference. Well, the difference is this one plus k. So if it's positive, then it will miss, right? It will miss. Because everybody will do positive. If this one do positive, the positive thing is not in there yet, then we'll miss. But we do negative, we do minus, because the sum will, but the sum, the numbers can be negative. The sum can get smaller and smaller. Or the k can be negative, right? If the k is negative, and for minus k, we're looking for something bigger, but we don't have. And keep going, so we keep trying to look for something bigger. hold on. I want to sum up to a negative value. If it's all positive, it's not possible, right? So if we want to sum up to a negative value, then they have to be negative. If the negative sum up to a negative value, as them going up, it will be more and more negative. And minus will be positive. Oh yeah, it still works. Still works. So minus will always work. Plus does not. Plus I need to have everything in place in order to use plus k. But if we do minus k, we can go to one by one. That is a good solution. Let's code it up. I think that's a good solution. Okay, but so this is the official solution, right? This is the official solution. This is from the official solution. Same idea, but its implementation is more intuitive and does not have to battle the edge cases. So we don't do this. We have the rest. We did the counter. Equals counter. And we're going to put a 0 in there. And then, so rest and the pre-s pre-sum, both are 0. Then for n in nums, right? We say ending at this. So anything previous. Yeah. Anything previous. Even the 0 works. Because when I do previous, I don't count myself. Oh, that's the trick. Because here, I already count everything. That's why I have to minus. But here, I'm going to plus. Now it makes more sense. So that's going to be plus equal to counter num n minus k, right? And then counter, and then, hold on. It's pre-sum plus equal to n, right? And then this is pre-sum minus, and then counter pre-sum plus equal 1. And then we'll return rest. I think this is, yeah, I think this is fine. Okay, let's run this. Yeah, I think it's good. Similar. Yeah, but this one is more intuitive. I agree. It's way more intuitive. Okay, so that's that. Done. Alright, we have time. Let's try another one. Wow, we're doing a lot of trees these days. Given the root, return an array of the largest value in each row of the tree. Oh, very interesting problem. I like it. I like it immediately. Well, we can definitely do BFS for this. Yeah, I think it's just BFS. But isn't that gonna be O? No, that is still O. That is still ON. No question. It's ON. Okay, so res equals this. Q equals root while q temp is this, rest dot append max q for node. Oh no 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 no. Rest dot append. We want to find the maximum value, right? And number of nodes, maximum next. So we have to do port math. So I would like to have math.inf, but negative math.inf. So for node in queue, right? Rest this equals maximum. Rest this node.val. If node.left, temp.append, node.left. If node.right, temp.append, node.right. Q equals temp, return rest. Okay. I didn't test the empty case. Yeah, I was like, I forgot to test that. Shoot. I was like, by the time I click it, I realized I forgot to test that case. Can we do something about it? Yep, just say if not root, return this. Yeah, could have finished this without triggering this issue. My bad. All right, so do we have a better solution than this? Is simple BFS. But pay attention to the edge case when root is empty. When 90. Why is it so bad? No, not 90% ranking. It's only 11% ranking, man. Yeah, why so bad? I mean, take a look at a good solution. What else can we do in addition to? Yeah, BFS or DFS. Divide and conquer. (2017). Kid in node for node in row. Yeah, that's fine for node in row and for kid in this. If kid, we put it. That's actually another way, much easier way to do. Maybe you want to do it this way. While any row. How do you do DFS? Uh-huh. Oh, I see. Yes, yes. Each time you reach a new depth, you append to the array. And then every time you reach the same depth, you just, yeah. D equals, and or, X. Yep. DFS can work. Divide and conquer. I mean, this is O(n). So I would say this is O(n) log n. As you divide, this is the merging. The merging is O(n). I'm actually gonna write the, is it still loading? Jeez. I want to write, let's write the DFS version. No, this is for practice purpose. Always good. Okay, so this is DFS inspired by, this is post. Okay, inspired by this. Okay, so def DFS, we have a node, right? Tree node, and depth. We need depth. Now we don't have to return anything. Just none. And if not node, we just if node. Now we just if node. And then we need a result. It's going to be this. So say if node, right? And then when we see the depth, right? We say if res len res is equal to depth, then res.append node.val. Else, then res it should be depth, right? Res depth equals to maximum. Res depth and node.val. And once we're done, we just do DFS node.left depth plus 1, depth right, depth plus 1. We're done. We call DFS root 0 and then return res. Okay, run this. I think it can handle empty case as well. Yeah. Oh, faster. And for sure, DFS, because you handle the stack is handled by the language itself, which is supposed to be faster than running a loop yourself. I think I've been very lucky these days. For the past few days, it's all trees, and I'm usually pretty good with trees, and I like trees a lot. So yeah, I think I'm in the territory of trees. Which is fine. Just keep solving it. Alright, that'll be it for today. It was a good one. I'll see you guys tomorrow. Adios.